This is joint work with Simon Mountakis. He's a PhD student currently in Greece, frantically trying to renew his passport, but he didn't make it on time, so that's why I'm here talking to you. And the other author is Cees Witteveen. He's the head of the algorithms group in Delft. So I'll be talking about revisiting temporal flexibility. We've in this paper revisited some results we've obtained in previous papers on regarding temporal flexibility. So I'll explain some of those previous paper results first, and then go to revisiting them. It involves flexibility in scheduling in the context of a simple temporal network. So this is a framework. I think I can go over this fairly quickly. Framework for capturing temporal information in the form of a bunch of temporal variables and constraints defined upon them, which is a special case of the general temporal constraint satisfaction problem. Oh, see, I'm missing some. I have no idea how to. Do you have any idea how to fix this?
I don't think we can play with the resolution.
It was okay just now, right?
Was it?
Yeah, when you showed it the first time.
Okay.
Very good. Thank you. Thank you. So an STN is defined as a pair TC, where T is a set of temporal variables. You have n temporal variables that you can use to capture, describe whatever domain you're reasoning about. And then there's the special T0 variable, which is often called Z, because it's always assigned to value 0. So you solve an instance of the STN, and then everything is linked to this temporal variable Z, and then that gets the value 0. So if you put that to a specific date and time in the real world, then this gives a value to all the other variables. And then there is a set of constraints which have a particular form. They limit the difference that can occur between the values assigned to pairs of variables to be at most some value D. And you can also use this T0 variable for expressing unary constraints, which otherwise you couldn't, because the constraints have to have this form of a difference between two variables. And minimum time lags can be just rewritten in the required form like this. And if you have both, then you can just say that the difference between variables is between some values C and D, or it lies in the interval from C to D. So here's an example of an STN. It's taken from a PhD thesis of a former PhD student in our group who received an award for his PhD thesis last year at ICAPS on simple temporal reasoning. So this involves making breakfast, so that's the B on the right, and then you have the eggs, making the eggs the start of and the end actions for or time variables for starting and ending preparing the eggs, and the coffee takes between 2 to 3 minutes at the bottom. And the eggs and the coffee get cold in 5 and 8 minutes, so you don't want to wait too long before you have breakfast. So the question is, and a different way of looking at this information is to break up these constraints which involve an interval into two constituent constraints, and then have the maximum temporal difference between these two on arcs that go from each variable to the other, where we drop the arrows that have that are unbounded. So that's called the distance graph, and you can use this distance graph to do some inference, because constraints imply other constraints. If the difference between I and j is at most 10 and between j and k is at most 5, then this implies that the difference between k and I is at most 15. So you can do this implication by, or you can derive these implied constraints by reasoning on this distance graph. So then you take the values that are on the edges as really the temporal distance between, the maximum temporal distance between variables. And you can compute all the tightest constraints implied by the given constraints in C by running an all pair shortest path algorithm in order n cubed. It is a cubic time operation in the number of variables. And then you store all these things in the distance matrix. Actually, the PhD student I mentioned improved this algorithm in a paper and in his PhD thesis. So you record all these values in the distance matrix, which gives the tightest bounds on the differences between between all pairs of variables. So on the diagonal, of course, all the values are 0. And one thing that this distance matrix immediately gives us is the earliest times you can assign to the variables, which is then the negative of the values in the first column. Because if, let's say, the -4 in the fourth row says that z can happen at most -4 time units after the ending the eggs, which you can rewrite as saying E has to happen at least 4 time units after Z. Because ending, that means you've cooked the eggs and they're ready. It means you have to have started cooking the eggs at time point Z 0. And it also gives the latest times you can assign to all the variables as the values in the top row. Because if that says that ti minus z is smaller than some value in the top row, then it just means that z is 0, so it's just ti is smaller than or equal to that value, the corresponding value in the top row. So this is a convenient way of representing this information, and this is something we're capitalizing on in our work. So one of the things we want to do if we have an STN is to find a schedule or an assignment of values to these variables that satisfies the constraints. So that's what a schedule does. But a schedule, or at least a fixed time schedule like this, is in practice, it's often not so useful, because during the execution of such a schedule, all sorts of unexpected disturbances and circumstances may occur that invalidate the schedule. And then if you recompute this, and then, in a sense, that's not so hard, but we use an STN as for describing a solution to a much harder problem in the work that we're doing with a company, which is RCPSP, and then getting a new schedule becomes much harder because you have to first derive another STN. So the solution that we use, I won't say that we come up with because that's quite popular to do this, is to assign not individual values to these variables, but to assign intervals of values to the variables, so that if it turns out you can't use the originally intended value, you just pick another value from the interval. And what we want to do is to have such an interval schedule. Essentially, having this interval gives you sort of a freedom to choose. We call this flexibility. So the flexibility of a schedule we measure as the sum of the lengths of all the intervals assigned to the variables. And of course, what we want to find for a given STN is a schedule that has maximum flexibility. So you maximize, and then the flexibility of the STN itself is defined as this maximum over all the possible assignments of intervals. So which intervals should we use? We know about these intervals between earliest and latest start times, but it's not really, it doesn't make much sense to use that as saying that's the flexibility. For example, you can, in the example I showed previously, you can start cooking the eggs at time 0, but that's incompatible with having breakfast at time 15, because it's just, the eggs will cool down too much. You didn't want that. So the choices that you make from the intervals from the different events, from the different time points, they're related to each other, and you have to take this into account. So here's an example that illustrates this very easily. So on the left, there is 3 concurrent events which have to all be scheduled in some window, and they're unconstrained, or at least, well, not beyond saying that they have to happen between t is 0 and t is 50. And on the right, there is a situation with sequential events where the first has to happen before the second and the second before the third. So there is there are dependencies between the times you can assign to these variables. But the earliest and latest start time intervals are the same for all events, both left and right. So if you use that as the measure of flexibility, then you overestimate the flexibility, at least on the right, that's really available. So we call this the naive flexibility metric. So what we came up with was, or what we wanted to do, was to assign intervals in a different way, namely in such a way that for every variable, you can pick any value from its interval, and then the combination of all these values for the different time variables constitutes a schedule, so it satisfies all the constraints. So we want these intervals to be independent of each other in a certain way. You want to be able to pick the values from the intervals concurrently, but that's why it's called concurrent flexibility. And it turns out that you can do this rather easily, or compute this such an interval schedule that maximizes this total flexibility of the schedule rather simply by solving this LP, where you maximize the sum of the differences, sum of the lengths of all the intervals, and well, the lower bound for each interval has to be smaller than the upper bound, of course. But the last constraint is the one that's the most interesting here, which says that for every constraint in the original instance, if you want to schedule a variable j after a variable I, and you assign the intervals to them, then the lower bound of the last variable has to exceed the upper bound of the second variable has to exceed the lower bound of the first variable by no more than this constant c. If you do that, then you know that whatever value you pick from these intervals, you cannot exceed this value c that's given in the constraint. So that was the solution. Now in this current paper, we're revisiting this. So I'm actually ahead of my own schedule now. So first I'll try to give a more, this is an interpretation, a geometric interpretation of what I've been talking about, which we used in a different paper with AAAI last year to sort of generalize these things to general systems of linear constraints rather than just temporal, these simple temporal constraints. So what you see, the large hypercube is the polytope for all the solutions to the situation on the left in the two examples I had, right? The three events that's scheduled concurrently. So you can pick any value in this hypercube. And it's also the value that is estimated, so it sort of measures the flexibility you have in that situation on the left. But as I said then, it also measures the flexibility you had in the situation on the right, whereas the polytope that has all the solutions for that situation is only the shaded polytope in this figure. So the naive flexibility is sort of the smallest hypercube enclosing the polytope of all the solutions for the constraints in this set C. And the concurrent flexibility metric that we're introducing, or that we have introduced actually, is determined by the largest hypercube that's enclosed within the polytope. So the advantage of using that is that you know that any solution that you pick within this hypercube, so the smaller one, the green one, is a valid solution for the scheduling problem. So you see that that it does what intuition suggests, right? It gives the first third of the time period between 0 and 50, gives it to T1, because it's all the way against the plane for T2 and T3, defined by T2 and T3. And it gives the second third to T2, because it's halfway that axis, and it's all the way at the top, because it gives the third to T3. And it says these are the intervals assigned to these three variables, and then within these intervals you can pick any value you want, and anything goes, which is because it's enclosed within this polytope. So that made it easy to reason about some of these things. So something else that we did is we made some alterations to this distance matrix. Because the distance matrix gives values that may be smaller than the C values in the original constraints in the STN. So you might as well, in the linear program we formulated, you might as well use the distance value matrix values, which we do there, and say that the difference between this upper bound of the one variable and the lower bound of the other variable cannot exceed the C value. Well, actually, it can't exceed the D, the value in the distance matrix there. But if you use this, then you have to say that Ti and Tj are unequal to each other, because that's the values on the diagonal, and those are all 0. So if you want to do this for Ti is equal to Ti, then you're saying that the length of the interval assigned to Ti can't exceed 0, which is, of course, not what you want. So we modified this distance matrix by saying we replace the zeros on the diagonal just by the difference between the earliest and the latest starting time, right? So we know it has to fall somewhere in between those. So the whole interval has to be a subset of the interval of earliest to latest starting time. So we'll just say, we'll just put those values on the diagonal, and then we get sort of a neater formulation for this. And we call this distance matrix D star, right, which is the same as D, but it has these other values, these larger values on the diagonal. And then it turns out that using this D star value, the values in that matrix for the weights of a certain weighted complete graph that you can specify, you can recompute, do essentially the same computation of these naive and these flexibility metrics by computing matchings in this graph. And I just put the results here on the slide, and of course the details are in our paper. So the concurrent flexibility metric is the minimum, the cost of the minimum matching in this graph, and the naive flexibility is exactly the cost of the maximum matching in this graph. And because you can do this now via computing matchings in a graph, this is much more efficient than computing a general linear program. So for this situation, that would take, the linear program would take approximately order n to the 5th time, whereas this computation via these computing matchings takes cubic time. So those are the results I wanted to talk to you about. So thank you for your attention.